All right, so part A. Part A, balanced binary search trees. Search. So these two things. So on top of the binary tree, we need these two properties. Search property and balanced property. All right. First, let's just go through the simple basic properties of binary trees. We need to store data in a binary tree. So organize our data in a nice structure. So then when we do data processing, some of the operations can be very fast. That's the reason we do, the special way arrangement. For example, heap is an example. We have many properties for a heap. So in order to get that special property sort in heap sort, we need that kind of properties. Yeah. You just use that as an example, but now we try to go to the general case. All right. Components in a typical binary tree, general binary tree, a finite set of nodes that can store data. Yeah. We store data in nodes. Yeah. Finite, not infinite. Yeah. That's simple. Root, that's the starting point to access data. Where do you start? You cannot start anywhere other places. You can only start from that root node. For other places, how do we access? How do we access a node other than the root node directly? Yeah, so that's why we need to always start from the root. Yeah. Internal nodes, the concept, nodes with child nodes. External nodes, leaf nodes. Yeah, so we just discussed. So we know that these two concepts. Then subtrees, left subtree and the right subtree. Yeah. Because usually when we consider left subtree, right subtree, each one also a binary tree. So then we can do recursion. Okay? Yeah. So to process the data structure, binary tree data structure, most of the time we use recursion. Yeah. All right. Properties of a binary tree. Yeah. Some more properties. Yeah. For a general binary tree, each internal node has at the most here, at the most. Okay. So that means could be 0, 1, 2. Okay. For the general case, 0, 1, 2. Could be 1. Okay. Yeah. Could be 1 child node, because it's general. Yeah. For full binary tree, yeah, we have that full binary tree. Then we cannot have that 0 case. Full binary tree. Okay. All right. A subtree of a binary tree is also, because we want to do recursion. So we use this basic fact. Okay? Yeah. Recursively to traverse the whole tree. Yeah. For full binary trees, the number of external nodes is 1 more than the number of internal nodes. For full binary, this property is very important. So the basic, very important. Yeah. So here, we learned this before. Can we prove it? We haven't proved it. Yeah, because for this class, we do not have much time. So sometimes we need to save time. So I do not prove it in this class, but this property can be proved by mathematical induction. So if you're interested, so you can Try it by yourself, although it is not required for this class. All right. The relationship between the height, h, so here, I think you know the concept, height of a binary tree, and the number of leaf nodes, L, there is this inequality. Oh, yeah, right. So here the height, definition, the length of the longest path from the root to a leaf, longest path. Then we use that as the height measure, okay? Yeah. So the inequality is this, L less than or equal to 2 to the h power, or we take log, ceiling function, we have this inequality. Yeah. So this inequality is true for general binary tree, not necessary for binary tree. So any binary tree. Yeah. But here, another thing I like to point out, when we talk about this height here, we mean the height of the whole tree, whole binary tree. But sometimes, so some of the questions I'll give you in the homework number 2, sometimes when you draw a binary tree, we can also talk about the height of a node, height of this node. Now we need to consider a longest path from this node to a leaf node, longest path. Yeah, not the, shorter than longest path. You have to use the longest. So we also have concept, height of each node. There is a height. Yeah. All right. Full binary trees. We learned this. Yeah. So in decision trees, remember, we learn decision trees. When we learn decision trees, each decision tree corresponds to a full binary tree for comparison sort. Remember, so when we do that comparison sort, okay, why I emphasize this, because for comparison search, then its decision tree is not necessary corresponding to a full binary tree. No, binary search, consider binary search. Yeah. Usually its decision tree does not correspond to a full binary tree. Yeah. So that's why we need to separate. Yeah. All right. So the full binary trees definition, a binary tree that satisfies the condition every node has either 0 or 2 children, but cannot be 1. Yeah, so that means the full. Okay. Properties, that property, the number of leaves must be 1 more than the number of internal nodes. Yeah, so this is a big property. Yeah, so we emphasize it another time. The number of total nodes must be an odd number. Yeah, because you add these two together. Okay, so internal node, let's say E plus leaf, right? Yeah. Sorry, internal, external. So I, internal, plus external, right? So that's the total nodes. But E equals I plus 1, right? Internal, 1 more than total internal, so equals 2I plus 1. So that is an odd number. Yeah. So very easy to see that property. Yeah. Next, binary tree traversal. After we have a binary tree, we need to do traversal. We need to, go through all the nodes in that binary tree without missing anyone. How can you do that? Right? For the arbitrary possibility, you can do that. Yeah. So here, there are three basic ways to do the traversal. Three types of traversals. First, pre-order traversal. Okay, pre-order, the name of it. The root is visited before the left and the right subtrees are visited. So we visit the root first, then left subtree, right subtree. Yeah, in that order, we call it pre-order. Yeah. So the code like this. Okay, the function traversal, pre-order traversal function. Okay. So when you visit the current node, so here, because we assume we start from the root, yeah, the current node we treat it as a root node. So we process the root node first. Then it's the left subtree, right subtree. Yeah. So here I use the C++ style. Yeah. This part I took from CS3250. Yeah. So when I taught CS3250, so I used this part. Yeah. But for our topic, for this basic, review, we just, review the older knowledge. Yeah. In order traversal, root is visited after visiting its left subtree before visiting the right subtree. Yeah, in the middle, between. Yeah, in between. Yeah. In order traversal, so let's visit left subtree first, then process the root node or the current node, and finally right subtree. Yeah. That's straightforward. The last one, post-order traversal. Yeah. So the root is visited after visiting left and the right subtrees. Yeah. Just like this. Yeah. So straightforward. Yeah. But based on your application, so which one we should use based on your application? Sometimes there is one of the three gives you the best solution. Yeah, you need to select. Yeah, you need to closely examine your application. For example, so there is an application, processing math formula. Okay, then in that situation, post order. Yeah, because you need to parse. So you need to use a data structure stack to store your math symbols. You need to choose one of the orders to, yeah. All right, so let's do not go that far. And we finish this introduction part. Yeah. Next, so let's learn more specific properties.